Okay, let me lay out the scheduling problem and also the mixed integer linear programming formulation, which I believe is more efficient than dynamic programming. That's the first thing I'm going to do. The second thing I'm going to do is show the most general dynamic programming problem that can be solved. So these are the problems that dynamic programming can solve, but mixed integer linear programming cannot solve. So the big question is, are these additional problems practical and important to solve? And if so, then dynamic programming is worth looking into. All right, so the scheduling problem. So here, let me just say that the simple scheduling problem, and I'll call this the scheduling problem with late time penalty. And this is a common problem that you'll see in the literature. So here's how it's formulated. So let's make this clear. All right. So we're given jobs, 1 to capital J. Now, you'll notice that I use capital J and small j. I use capital letters for total numbers that are fixed. I use small letters for running indices. So the index small j runs from 1 to capital J. Now, when you're talking about it, it may be a little confusing. I typically refer to small j and cap j, but I like doing it this way because it cuts down the total number of variables, and it also makes it clear which index relates to which quantity. So you know right away that small j indexes a job because jobs are numbered by capital J. All right, so we're given capital J jobs. The job durations are delta 1 through delta j. So I chose this notation delta to emphasize that delta is a duration and it's not an absolute time. So it's not Tuesday at 4 p.m. It's 6 hours or 7 hours. That's how long the job takes. Now we also have the job deadlines. These are fixed times, D1 through DJ. All right, so deadline is D, duration is delta. All right, I hope that notation makes it easier to remember. Now a schedule is defined as an ordering of jobs. No, ordering of jobs is simply a permutation. And a permutation is a function from the integers 1 to j to itself. So it's just a rearrangement of the first capital J integers. Now, each job has a deadline. So the deadline of the jth scheduled job, well, the jth scheduled job is going to be sigma of j because that's the actual job that's in the jth position. All right, so if I want the 5th job that's scheduled, I'll take sigma of 5. All right, so that's what sigma does. It matches the position to the actual job that is scheduled to that position. So the deadline of the jth scheduled job is cap D of sigma j. Now, the time at which the jth job is actually completed is what? Well, the first job scheduled is going to have a duration of delta sigma of 1, right? Because sigma of 1 is the first job scheduled and delta is duration. Now, after that, job 2 is begun as soon as job 1 is completed. So you have to add the duration of job 2. Similarly, add the duration of job 3, all the way add up to the duration of the jth scheduled job, which is sigma of j. So the time at which the jth job is completed is the sum of these durations. Now, what's the penalty? Well, the penalty is the amount of time that it's late. All right. So I call that Pj. The penalty for the jth job is Pj, and that's going to depend on the permutation sigma. And that's the maximum of the actual completion time Tj minus the deadline. All right, it's the difference of these two terms. I take the maximum of this in 0 because there's no advantage to completing early, but there's a penalty to completing late. So if Tj is less than d sigma j. That is, the job is completed early, there's no advantage. But if tj is greater than d sigma j, then there's a penalty. Now the total late penalty will be the sum of all these late penalties for all little j jobs. All right. So the overall problem is find sigma such that this should be a p, sorry. I changed the notation. pj is minimized. All right. So that's the general scheduling problem with late time penalty. Now I mentioned that linear programming can get a better solution. In fact, the technical name for the type of program is a mixed integer linear program. And it's called mixed integer linear programming because some variables are integers and some variables are continuous variables. So let's see how this works. Now, what I'm going to use is, this is a common strategy in mathematics, I'm going to use something called an indicator variable. An indicator variable takes values of 1 or 0. You may know this as a Boolean or logical variable. Okay, that's often used in programming. All right. So my zjk is 1 if the jth scheduled job is k, and it's 0 otherwise. So when I look at these zjks, I can tell which job is scheduled at which position. All right. Now what I want to do is reformulate the scheduling situation in terms of these z's. All right. And that's actually, when you look at it the right way, that's not too difficult to do. So what is the due time of the jth scheduled job? Well, we define that above as d of sigma of j. That's the due time of the j scheduled job. Now I can express this, in fact, as a linear combination of the z's. Remember that zjk is only 1 if sigma of j equals k. So if I take the sum over all jobs of zjk times dk, well, what's this sum going to be? It's going to pick out exactly one term. It's going to pick out only the term where sigma of j is equal to k, which is exactly going to give me d of sigma of j. Right? So I've expressed the due time of the j scheduled job as a linear combination, i.e. a linear function of the jk's. That's a good thing because linear functions are good. All right, now I also want to find the actual completion time of the jth job. So here, let me just make sure this is equal to the equals the due time of jth job. Now tj is the completion time. And I should say the jth scheduled job. All right. And this is the completion time of the j scheduled job. Remember, the j scheduled job is actually sigma of j scheduled job. So what do I do? That's going to be equal to the sum of the completion times of all jobs up to, that's going to be the sum of the durations of all jobs up to the jth scheduled jobs. Okay, so let me write another line here. That's going to be equal to the sum of completion time of the durations of all jobs scheduled or I can say of the first, second, jth job scheduled. Okay. Right, because the time at which my third job is completed is the duration of the first job scheduled plus the duration of the second job scheduled plus the duration of the third job scheduled. All right. Now, if you think about how to express that in terms of the z's, the duration of the the duration of the kth job scheduled is going to be the sum over all jobs of the duration of that job times the indicator function. And I'm sorry I made a mistake here. This should not be a subscript k, it's just sigma L. Now what's inside this sum here? This sum here is what? I claim that what's inside this sum is the duration of the kth job scheduled. All right. Because what I've done is I've summed over all durations times zkl. The zkl is going to pick out the kth job, so zkl times delta L is going to be delta k. Okay. Or I'm sorry, it's not going to be delta k, it's going to be delta of the kth job scheduled. It's going to be delta of sigma of k. All right. So you think about that a little bit, but that's how you can get the sum of the duration of the first j job scheduled, and that will be the completion time of the j scheduled job. Now, what I have is a very good situation now, because I've expressed both the completion time and the due time as linear combinations of the zjk's. So I only have linear functions involved, and linear functions are very useful. By the way, what I mean by linear is it is a constant times the variable. Now, there's no powers of variables or other functions of the variables. It's just a constant times the variables. And my variables are these zjk's. So in summary, my mixed integer linear programming formulation is to minimize the sum of penalties. Now I have conditions on these zjk's. This one says, this condition here says that only one job is scheduled at each time. Or I could schedule at position k. And this one says that all jobs are scheduled exactly once. So those are constraints on my z's. And these are also linear constraints. These are linear functions of my z's. Now my penalty, I write my penalty this way. This is my penalty function. This is my completion time minus my due time. And these are both linear functions. And I put a greater than or equal to, because if this quantity is negative, then I don't want to set this equal to the penalty. So I have this condition, penalty is greater than or equal to this difference, but penalty is also greater than or equal to 0. And I also have the condition that zjk is either 0 or 1. So these conditions hold for 1 less than or equal to j and k less than or equal to n. So you can see that this is a very concise formulation here. And it turns out that the solution algorithms for this problem are quite a bit better than the solution algorithms for dynamic programming. Now, however, this mixed integer linear programming formulation works only if the late penalty is proportional to the late duration, or the late interval. Why don't I say late interval? Whereas dynamic programming can handle any late penalty. For instance, suppose I'm 1 day late, I have a penalty of $10. Suppose I am 2 days late, I have a penalty of $100. Now, the mixed integer linear programming formulation cannot handle that, but dynamic programming can handle that. So I thought a little bit about the most general problem that's solvable by dynamic programming, and so let me list that here. So I think maybe I'll make another video for that. That's probably better.